All right, so today we're going to be talking about how to identify quadratics and how to graph parabolas by factoring. Remember, parabolas are the graphs of quadratic functions. So here are three different functions that we will be using throughout this lesson. We're going to be talking about linear functions. Again, we typically see it in slope-intercept form, y equals mx plus b. In the middle, we have what's called an exponential function, which is in the form of y equals ab to the x. We're not going to be graphing this. We're not going to be talking about it much, but it will come up within the lesson. So I just want you to see that this is an exponential function. And then what we're going to talk about today is the quadratic function. Again, is written typically as y equals ax squared plus bx plus c. So without further ado, let's talk about a key concept here. So we're going to be looking within tables, and what I want you to focus on is the stuff that's written down here. Oh, I got to move this up for you. So if you're given a table or you're given a set of coordinate points, we can determine what that set of coordinate points is going to look like. It's going to be either a linear function, an exponential function, or a quadratic function. For a linear function, the first differences are going to be constant. For an exponential function, the consecutive y values have a common ratio, aka I can multiply by 2, by 3, by 4 every single time, and it's going to be the same ratio. And within a quadratic function, which is what we're going to be talking about mainly today, it's the second differences that are going to be constant. So let's just show one of each next. So we're going to be working with these three tables. This is A, B, and then C is all the way down here. So let's talk about A and B and determine whether or not it's going to be linear, exponential, or quadratic. So we look at our change of x's, and it's going up by 1. Every single time is going up by 1, which is great for us to start out with. And we want to see, is there a common ratio going within our y's? Or is there going to be a common difference? So if I'm going from 11 to 8, I'm losing 3. 8 to 5, I'm losing 3. 5 to 2, losing 3. 2 to negative 1, I'm losing 3. So this is going to be linear. Remember, we call it has a slope of negative 3. So this is going to represent a linear function. We have seen this before, and you've done so well with it. Okay, let's go down to B. Well, again, we're seeing we have a change of 1 in my x's, which is great. And now let's see if we have either a common ratio or some differences in my y values. Well, I'm seeing that my y, I'm increasing by 1, I'm increasing by 2, I'm increasing by 4, I'm increasing by 8. So I don't really see a common difference at all. So let's see if they have a second common difference. Well, from 1 to 2, I'm adding 1, 2 to 4, I'm adding 2, 4 to 8, I'm adding 4. So I don't have a common difference in the first set nor in the second set. So now we want to see, okay, is there a common ratio? So if I want to multiply, how do I go from 1 to 2? Well, I times by 2. 2 to 4, I times by 2. 4 to 8, I times by 2. And 8 to 16, I'm multiplying by 2. So this is going to be an exponential function. And again, we don't need to graph this. We're not going to be talking about this until later in the year, but just want to expose it to you. Expose them! So now let's talk about C. Well, again, every single time in my x's, I'm adding 1, so it's perfect. And now let's look at my change in y. Well, I wanted green, thank you. Well, I'm subtracting 1 here. I'm now adding 1. I'm now adding 3, and I'm adding 5. So now we see, okay, is there a common difference in the second set? Well, from negative 1 to positive 1, I'm adding 2. From positive 1 to positive 3, I'm adding 2. 3 to 5, I'm adding 2. So since there's a common difference in my second set, this is going to be a quadratic. Awesome. So to find a quadratic, we can see if there is a common difference in the second set. So that's explained from the prior slide. And I just wanted to give you a quick visual as to how to tell the difference between a linear, exponential, and quadratic function. Another thing we want to talk about is how to identify zeros in a quadratic function. So within a quadratic function, there's going to be three opportunities, or three different possibilities, I should say. Either it's going to have 2 zeros, 1 0, or no zeros. When we're dealing with 2 zeros, notice that we're looking for 2 spots where the parabola goes through the x-axis. So it happens twice over here. If you look at the 1 0, well, it only, nope, I wanted green. Come on. There we go. Notice that it only goes through the x-axis at one spot. So this function right here would have 1 0. And notice how in no zeros, I can highlight the entire x-axis and the parabola does not hit it, meaning that this function will have no zeros. So if you're given a graph and they say, okay, how many zeros does this function have? All you need to look for is it going through the x-axis how many times. If it goes through it twice, it has 2 zeros. If it goes through it once, it has 1 0. If it doesn't go through the x-axis at all, it has no zeros. And that is how to go from a 0 to a hero. Hercules shout out there. So now let's talk about how to actually graph a parabola through factoring. Okay, and again, we are going to be going through factoring. Oh, there we go. So let's talk about this first example. Graph the function f of x is equal to x squared plus 6x plus 5. Over on the right-hand side, I'm going to continue that box now, is a checklist. There's 4 things that I want to have in order to graph parabolas through factoring. I want to find the x-intercepts, the y-intercept, the axis of symmetry, and the vertex. So let's go through all 4 of them together and then graph it, and then you are going to try one on your own. So let's find the x-intercepts. Well, we can do that through factoring. If I have x squared plus 6x plus 5, I can factor that. I'm going to rewrite it, x squared plus 6x plus 5. I'm going to set it equal to 0 because I want to find the zeros of the function, and we can do that through factoring. Well, we want to find factors of a and c that add up to b. So factors of 5 that add up to 6, well, I get x plus 1 and x plus 5 equaling 0. Therefore, I have x is equal to -1 and -5 using the zero product property. So my x-intercepts, I'm going to write over here, x-intercepts are going to be -1, 0 and -5, 0. Those are my x-intercepts. Awesome. Nice job. Sweet. Let's look for the y-intercept. Well, the y-intercept is when x is 0, or we just look for the constant term. If we look at our equation, this 5 is chilling all by itself. That's going to be our constant term. The term that's chilling all by itself is the constant. So I have my y-intercept, again, is when x is 0. It's going to be 0, 5. So this parabola is going to be going through the y-axis at a value of 5. To find the axis of symmetry, we have 2 different ways to go about it. So what we can use is what we've talked about before. We have, nope, I wanted a different color. Come on. So we have this handy-dandy formula, x is equal to -b over 2a, and we can definitely use that. Let's plug in our values. Well, our b is 6, so it's going to be -6 over 2 times 1. We get -6 over 2 is equal to -3. So we know that our axis of symmetry is going to be x is equal to -3. There's another way to go about it though. Since parabolas are symmetrical and we found the x-intercepts, what we can do is actually take the middle of our x-intercepts, or we can take the average of it. So if we want to take the average of it, well, our x-intercepts are -1 and -5, so -1 plus -5, and there's 2 quantities there. So it's going to be -6 over 2, which is also equal to -3. So if you're just trying to find the vertex from the start, then you can use x is equal to -b over 2a, But if you have the x-intercepts, you can just find the average of them, or just find the middle value between them by adding them together and dividing by 2, and you still get the same answer. So now we need to find the vertex. Well, we know the vertex has the x value of the axis of symmetry, so now we just got to plug in -3 and see what happens. So if I have x squared plus 6x plus 5, I'm going to plug in -3, so I get -3 squared plus 6 times -3. And we can simplify down, we get 9 plus -18 plus 5, and then we get 9 plus -18 is -9, -9 plus 5 is equal to -4, which means that my vertex, and I'll write it down here, is going to be -3, -4. So now we have all of these checked off from our checklist. We can go and graph it. So over on this slide, I've already transferred everything over, and we're just going to start graphing. Well, the x-intercepts are -1 and -5, that's 2, 3, 4, and 5. My y-intercept is 0, 5, so 1, 2, 3, 4, and 5. My axis of symmetry is x is equal to -3, so it's going to be right here. Just going to give a quick little axis of symmetry. Not perfect, but it gets the job done. And my vertex is -3, -4. So it's going to be on the axis of symmetry. I just got to go down 4. 1, 2, 3, and 4. So now we have the points. We can just graph it. It's going to look something like this. Of course, it's not perfect. Just disclaim that. It's definitely not perfect. Okay? But it gives us a good representation about the way the graph is going to look. Notice how it's opening up because my A is greater than 0, so it's opening up. Okay, perfect, great job. So now you try out this problem. Pause the video, attempt it, try and find the checklist items, and then see what the answer is. So here is the answer. Let me slowly scroll through. That way you can get the whole screen. So we find the x-intercepts would be 7, 0, and 1, 0. The y-intercept is 0, 7. The axis of symmetry is x is equal to 4, and the vertex is 4, 9. Here is the graph of it. Again, the x-intercepts are in blue, the y-intercept is in red, the axis of symmetry is in green, and the vertex is in purple, with the, again, not perfect graph in black. Awesome. Real quick, one last note. Okay, so here is the core concept that I'm going to show you, and then I'm going to summarize it in the next slide. It can get a little bit wordy and can get a little bit confusing when you're looking at everything here. But what it's saying is that if I have this, what we call the mother function, okay, it's going to be this one right here in blue. That's when A is going to be 1. Notice when A is greater than 1, okay, it's going to be skinnier. And notice when A is in between 0 and 1, it's going to be wider. And it happens the exact same way down here. When it's closer to 0, it's going to be wider. This is our mother function, and this is when A is going to be greater than 1. So again, this is just that note summarized. I'm almost out of time, so I'm going to rush through here, sorry. Okay, so if the absolute value of A is less than 1, it's going to be a wider graph. In black is the mother, so it's going to be wider. It's going to look something like this, or even like this. And likewise, if the absolute value of A is greater than 1, it's going to be skinnier, or it's going to be a taller graph. Again, in black is the mother, so it's going to look something like this, or it's going to look something like this. Great job, y'all. So proud of you.